Many concepts in organic chemistry make use of the idea of polarity, both polarity of bonds and polarity of molecules. Now, a polar covalent bond is what you get when the pair of electrons involved in a covalent bond is shared unevenly between the two atoms. And this is going to occur anytime you have two atoms participating in a bond that have a difference in electronegativity. Now, that strict definition would imply that any bond between any atoms of different elements is a polar bond. So we generally add the criteria that a bond is considered polar if the electronegativity difference between the two atoms is at least 0.5 electronegativity units. Okay, so a reminder of the electronegativities of the elements that are important for organic chemistry. Hydrogen has an electronegativity of 2.2, carbon is 2.5, nitrogen is 3.0, oxygen is 3.5, fluorine is 4.0, chlorine is 3.0, and bromine is 2.8. Okay, recall from general chemistry that electronegativity is the tendency of an atom to pull bonding electrons towards itself. Okay, so when an electronegative element is involved in a bond, it's going to want to take those bonding electrons and pull it in towards itself. So, based on our criteria, CH bonds are going to be considered nonpolar because the electronegativity difference is only 0.3. But carbon-nitrogen, carbon-oxygen, and carbon-chlorine bonds, which occur very frequently in the world of organic chemistry, are considered to be polar bonds. So when we're trying to indicate this on a piece of paper, we're going to use the bond dipole symbol on the very far right of the slide here to indicate a polar bond. And the way the bond dipole system works is that the arrow points towards the more electronegative element in the bond. So that means there is more electron density from that bond located in the vicinity of the more electronegative oxygen, making that the negative end of the dipole, and there is less electron density in the vicinity of the carbon, so the carbon is the positive end of the dipole. The symbol actually makes it clear to see this because where the two lines cross looks like a positive charge. Okay, not only are bonds polar, but molecules can also be polar. A molecule is polar if it has a permanent net dipole over the entire molecule. Now, in order for a molecule to be polar, it has to have polar bonds. The converse is not true. You can have molecules with polar bonds that are overall nonpolar molecules because the polar bonds all cancel out. But in the molecules that I'm going to show you below, there is a net dipole because the polar bonds do not all cancel each other out. Okay, so this molecule is called chloroform. It's got 3 carbon-chlorine bonds and 1 carbon-hydrogen bond. So we say that the carbon-chlorine bonds are all polar, and the net dipole for all of those carbon-chlorine bonds is indicated. The way this structure is drawn, of course, the 3 chlorine atoms are pointing down towards the bottom of the molecule. That is the negative end of all of the dipoles, so the net dipole for the entire molecule is pointing downwards. Another molecule that has a net dipole is acetone, which has a carbon-oxygen double bond. In this case, the net dipole is pointing upwards because the oxygen bears a partial negative charge and the carbon is the positive end of the dipole.